Okay. Hello, everyone. Today I will present generative image inpainting with contextual attention. So, as some of you might know, for the past year I have been working with on video completion with optical flow. So, mainly focusing on these two papers. But then in the summer project we worked a lot with deep learning. And it was also the time that I had to start thinking about what topic I would choose for my master thesis. So naturally, I asked myself if this video completion could also be done with deep learning. So I started to look for papers about this, but surprisingly, there are not many papers about video inpainting with deep learning, but there are a lot of them about image inpainting. And one of those is this paper, the generative image inpainting with contextual attention, which is why I chose this paper to present to you today. So this is the one that I will use as a reference paper in my master thesis. So when people started to do research into image inpainting, the main type of method that was used was patch-based. So the very first methods worked with patch similarity, where basically they looked for similar patches in the rest of the image that they could use to fill the hole. But these first methods, they worked really well for simple images like this with simple textures. But for more complicated textures like this, they didn't work very well. And later, Simakov et al., they solved this problem using a bidirectional patch similarity-based scheme. So the results for complex images were much better, but the problem was that it was very time-consuming. So in practice, this couldn't really be used for many applications because of the time. And then this time problem was solved by Barnes et al. In patch match, where they use a fast nearest neighbor field algorithm, which works much faster but still has very good results. The problem, however, with all of these patch-based methods is that they cannot generate novel image contents. So, for example, if you have a picture of a face and the nose is occluded, then these methods, they cannot recover the nose because there's no image of a nose anywhere else in the image. So then when deep learning became popular, naturally they started to think if maybe this problem could be solved with deep learning. And they started out really simple, using convolutional neural networks for denoising, where the region that needs to be inpainted was very small. But then later, using context encoders, they could inpaint larger and larger regions. And then finally, in 2017, Izuka et al. Published a paper where they used global and local discriminators and also dilated convolution that gives really good results. And this is the reference paper that, well, for this paper, they used this as a reference paper. There are also a few papers where they approach inpainting as an optimization problem. Then also the title of this paper is Generative Image Inpainting with Contextual Attention. So they use attention modeling to improve inpainting results. And in the past there have been other types of attention modeling used for other applications as well. So one is the spatial transformer network that was used to help with object recognition. But the problem with this is that since it's used for object recognition, it looks at the global picture, but for inpainting you want to look at local features because you want to recover details. So it doesn't work very well for inpainting. Then there's also appearance flow, which was used for novel view synthesis, but as will be later proven in this paper, this also doesn't work very well for inpainting. And then there were also some papers on learning spatially attentive or active convolutional kernels, which, according to the authors of this paper, could be useful for inpainting, but they think it will still be limited for recovering exact features from the background to the foreground. And then onto the proposed methods. So their baseline network is heavily based on Izuka et al. Paper. So just like that paper, they have a two-stage network. So they have a coarse network here that does a coarse prediction, and then a refinement network that improves on that coarse prediction. And they also have two discriminators. The network takes a 256 by 256 image as input, and also a binary mask. So you cannot see it here on the picture, but the image has 4 channels, so 3 channels for RGB information, and then 1 channel for the binary mask, so a 0 or a 1, that says whether the pixel needs to be inpainted or not. And then the first network is trained with the spatial discounted L1 loss, which I will explain later on. And then the second network is trained with this discounted L1 loss and also the 2 critic losses, which I also will talk about later. So first for the spatial discounted loss. So say that you have this picture that you want to inpaint, and this region you need to recover. With the spatial discounted loss, what they want to do is basically give the network more freedom. So when you need to inpaint like the region next to the edge, close to the edge of the mask, you don't have a lot of freedom of what you can do, because it needs to fit with the edge, with the rest of the image. But the further you go from the edge, the more freedom you can get, and the more you can diverge from the ground truth. And so they do this with this spatial discounted loss. So if we have, for example, this pixel, then they calculate it like this. So you have just your normal L1 loss, so the difference between ground truth and the prediction. And they multiply it by this term, which is 0.99 to the Lth power, with L being the distance from the pixel to the edge of the mask. So the further you get from the mask, the lower this loss will be, and the more freedom the network has to try something different. And then, as I said before, they have 2 discriminators. They have a global and a local discriminator. So the global discriminator takes the entire image as input, while the local discriminator only takes the inpainted region as input. But to train these 2 discriminators, they use the Wasserstein-Gunn with gradient penalty term. So, so the normal vanilla Gunn loss is like this, where you have X being the ground truth and X tilde being the prediction. But for the Wasserstein-Gunn, they simplify this loss function, and they just calculate it like this, so you can see that the logs have disappeared. And in past works, this Wasserstein-Gunn loss has proven to be better for networks that use image information as their data. But then finally, they also add this gradient penalty loss term, which is this term where they give another input to the discriminator, this X hat, which is basically an interpolation between the ground truth image and the predicted image. So it's calculated like this, with T being a random value between 0 and 1. And so adding this term, also again in previous works, it has proven to make the training process much more stable. And so this final loss function is what they use to train both their local and global discriminator. Yeah. Yeah. Yeah, yeah, and it has improved results. And then their main contribution is this contextual attention module. So, as I said before, they have 2 networks, but their second network is a bit more complicated. So the decoder part of the network is just a regular decoder, but the encoder is actually two networks that are parallel to each other. So we have one network which is a regular encoder, as is used in the course network as well. But the other network is a contextual attention network, which makes these attention maps, as they call it. And so an attention map is basically, it tells you for a certain pixel where in the rest of the image you can find a similar pixel that you could use for inpainting. So, for example, this attention map is for like this inpainted region. So if you have like a pixel here that has like this pink purple color, which means that you have to look in the left bottom corner. So for like this pixel, you have to look somewhere over here in the image to find similar pixels. And the way they calculate this map is using these beautiful functions over here. So the first one is basically so F and B are two patches, with F being a foreground patch from the inpainted region, and B is a background patch, so it's from the ground truth part of the image. And using this formula, they calculate a similarity score between these two patches, and then they use softmax to get a attention score for a single pixel. So this is to basically go from patch to pixel. And then finally they do something that they call attention propagation, which is basically that they assume that if you have a certain pixel in the foreground and the attention score says that you need to look to a certain pixel in the background, then pixels around that foreground pixel will probably have to look at pixels around that background pixel. Right? Yes? Everyone? Okay, anyway, so they do this a summation. Here it's for the x direction, but they also do the same thing in the y direction. And so this gives them the final attention score, which can then be shown using color coding, can be shown like this, like a sort of flow map. But all of these formulas, they implemented using convolutional layers so that they can actually make a network like this, which is more efficient. So then we have these two networks that work parallel, and they each get this course result as input, and then they each do their own thing, and then the output is concatenated and then given as input to the decoder, which gives us the final inpainted result. And then finally their training algorithm is very straightforward. Just as long as the generator network has not converged, they first train the discriminator, so they update them here 5 times first, and then they train their generator network, and they do this until the network converges. And then for some results, here they compare with their reference paper, Izuka et al. It's also important to note that with the Izuka et al. Paper, they need to do image blending after their network prediction, which is not necessary anymore in the proposed method. And so you can see here like that it has a slight improvement. And here they show some results they compare their baseline model with the full network. So this is without contextual attention. This is with contextual attention. And so again, you can see like that there are some improvements. And then here they show some different results for different data sets, so faces, textures, and then images. And also they show the attention maps. And then for some quantitative comparisons, they compare with patch match, and again their baseline model. And as you can see, their proposed method outperforms the other methods for L1 loss, L2 loss, and also peak signal to noise ratio. But for the total variation loss, patch match performs best. Honestly, I don't really know. Because they also don't really explain why they think this one performs better for this total variation loss. So, yeah. They also did an ablation study. So they compared the use of the W GAN with gradient penalty with other GAN losses, like DC GAN and LS GAN, and the result was that the training was less stable, and they also got worse results. And they also looked at if they could maybe remove the L1 loss and only train their network with the GAN losses, but again they got worse results. And they also looked at maybe adding some other loss terms in their function, like perceptual loss, style loss, total variation loss, but again there was no improvement. I do have to say with this that they didn't show any statistics or images, so we just have to take their word for it that it's actually true what they're saying. Anyway, and then finally they also compared their contextual attention methods with the other modeling, attention modeling methods that I explained in the related works. So first the spatial transformer network, which was used for object recognition. Here you have the two ground truth images, and then you see that even though the ground truth images are different, the attention map is actually the same. So it doesn't really work well for in this particular application. And then for appearance flow, the attention maps are quite good, but the result is not really good compared to the contextual attention. So here the proposed method also outperforms the other methods. Yeah, and this brings me to the conclusion. So in this paper, they presented a course to find a generative image in-painting network, where they introduced a contextual attention module, also spatial discounted reconstruction loss, and then global and local WGANs. They also mentioned that this method could also be applied for other applications like conditional image generation and image super resolution. One limitation of this work is the resolution of the input images, which is pretty small. And so in the future, they would like to work on high resolution in painting. And this is the end of the presentation. Are there any questions? Mm-hmm. Yeah, there are some other papers that work not really with in-painting, but just with videos and time consistency in general. And so there are some things there that I think like I could apply here and then see how the results are. So yeah. Or do you want like specifically what? Okay. Video domain. Yeah, yeah, yeah. Okay. You. Well, technically it's like in the code they have 5 channels, but it's like 3 red, green, blue, and then they have one which the one channel which is always 1, and then they have the lost channel which is 0 or 1 for their mask. So I'm not sure why they put this 1 in between. I think it's maybe just to like separate the two, but I don't know if that channel is absolutely necessary. But yeah, that's how they did it. Yeah. Well, it just. Huh? You mean just with a wide region, you mean? I think it's to make sure that if you want, like, because how could you know which part is actually needs to be removed or not. Maybe you want a white space to stay. You mean like just use like ground truth and then the I don't know, as far as I know, how I understand it, and also how I find it quite normal also that you give a mask to show like this is the part that I actually want to remove and this is the part that I want to keep. Because in the output they well actually that's a bit bad. Anyway, in the output they just use that mask to say like we keep the input of okay, I'm going to go back to so the output is actually they copy this and then this part, because actually if you don't like the output of the network is like completely generated like this, but they just cut out that part and keep the rest of the image, if you know what I mean. Yes? No? I have a feeling you don't, but okay. Mm-hmm. No, yeah, this is removed. It's put in, well here they show white, but I believe it's actually black in the code. But yeah, so they actually remove it, yeah. Okay. Anything else? Well, during the training, you mean about the mask or? Yeah, so they during the training it's always rectangular masks that they just randomly put somewhere. But you can I believe they fix the size of the mask, but the place is random. But how many? One? You mean how many like squares? One, yeah, one. Mm-hmm. Oh, you mean if they use the same mask for like their batch? So you mean if they use the same image with different masks for training? As far as far as I know, they just have like one image, one mask. But the mask is actually during training it's randomly generated. So if you train it again with the same image, the mask will be different. Yeah. I don't know, because actually they don't mention this at all in the text. It's just they have at the end they have like a little like box where they put their training algorithm, and then suddenly out of nowhere this loop appears. And I was like, okay, I don't know why they do it 5 times. I don't know. So they don't mention anything about this in the paper. Yeah. Anything else? Other questions? I think, wait, let me think. Because you can set, they have like a configuration file that they use every time with training, and there you can set the size of images and everything, and the size of the mask is also set there. But I have changed it so many times that I don't remember what they use. I think it's like 64 on 64 or something. Yeah. Well, they have a little bit of, so it's not always 60. For example, if you say 64 and 64, they change a little bit. So they take like a random number between a certain range that I don't remember, and then they subtract that from the size. So it will be something between a certain range all the time. Yeah, yeah. Yeah, apparently that was necessary with the Izuka paper. I don't really know actually. They just in the paper it just says like in that paper they needed image blending and we don't need that anymore. So I don't know why. Yeah, it's composite. That's what I actually meant earlier. Why they have this binary mask, because they use it to composite the part that is not that does not need to be unpainted, and then with the unpainted part. So, like the etch, let's say, is like the original input image. Yeah. Okay. Any other questions? No. Okay then. Thank you very much.